Developed an enhanced strong-arm latch comparator featuring a differential preamplifier and adaptive tail current control. So basically, we wanted to address and acknowledge the limitations of the previously established works, and we wanted to achieve high speed and precision and energy efficiency. So for that, we have designed 12-bit SAR-ADC, 12-bit SAR-ADC for application of that. So we have designed the strong arm latch according to that, so that it can take a decision smaller than 1 LSD. And we ran some simulations regarding these parameters in our circuitry to validate our proposed architecture. So moving on to the next part, it's the methodology. So as you can see, here's the block diagram of our work. So this block diagram shows a strong arm latch comparator with a preamplifier, a buffer, and an SR latch circuit. So let's talk briefly about the working functionalities of these blocks. So basically, the preamplifier amplifies the small input differences and reduces the kickback noise, as I mentioned before. The strong arm latch comparator dynamically compares two voltages, and it regenerates the signal to full rail-to-rail output whenever there is a transition of the clock or the clock goes time, because it's a circuit which works with the help of the clock signal. The buffer and the strong arm, the SR latch, basically it isolates the latch from the load. So whenever there is negative edges of the clock or lower voltage level of the clock, it just holds the output. Moving on. So basically, this is the strong arm latch structure that we have worked on. So as I said before, in a whole ADC, the comparator is a small part. It might be a small part, but it actually controls the performing parameters of the whole ADC system. So this is our strong arm latch, which is working as a comparator. And to understand this circuit, basically what we need to know is that the PMOS turns on whenever there is a low voltage in its gate, and the NMOS turns on whenever there is a high voltage in its gates. So these are the PMOS and these are the NMOS. So whenever the clock is low, these MOSFETs will be turned off, and since these are the PMOSs, these MOSFETs will be turned off. As a result, the voltage VDD will flow into these four nodes, X, Y, P, and Q. For your better understanding, I guess it's not visible enough. So this is this M1 transistor, M3, M5, and M6. So whenever the clock is low, these four nodes or nets are recharged to VDD. But whenever there is a positive clock, these NMOSs turn on. This is the tail MOS, and it just draws the current from the whole circuitry. So whenever the clock is high, these MOSFETs turn off, and as we know, because these four nodes are at VDD, whenever this MOS is turned on, there will be current flowing from these two branches. So we put two differential signals in these two gates of these MOSFETs, because this is the input pair or input pair MOSFETs in our circuitry, which control the circuit overall. So let us assume that we're applying more positive voltage than this one. So as a result, the nodes charged to VDD, especially P and Q, they will start discharging because there is a current flowing in that part. So P and Q are